Welcome everybody to this discussion session. My name's John Chapman. I'm a professor of applied mathematics here. My interests are in mathematical modeling and differential equations with applications in things like solid mechanics and fluid mechanics. And to my right, there's Ruth Baker. Ruth, why don't you tell people what you do?
Good afternoon. So my interests are in developing and applying new mathematical and computational methodologies, primarily for the study of problems in cell and developmental biology.
Mike Giles, Professor of Scientific Computing, working on the development and analysis of numerical algorithms for a variety of applications. I'm also the incoming head of department, started 2 weeks ago.
My name's Ben Green. I'm the Waynfleet Professor of Pure Maths and a Fellow of Magdalen College. And as the title suggests, I'm a pure mathematician, and my particular interest is in trying to understand problems in number theory using other areas of mathematics.
So we're going to talk, we're built to talk about the mathematics for the next 100 years, but as mathematicians, it's nice to have a data point or two before you extrapolate. So I'd like to start by thinking about what mathematics looked like 100 years ago. And so I'm going to ask Ben, what were the sort of problems that pure mathematicians were interested in 100 years ago?
Right, well that is not a question with a one-sentence answer, so if you'll give me a few minutes. So there are several ways you can try and answer that question, and I'd like to begin by mentioning a very famous list of problems that was posed at the International Congress of Mathematicians in 1900. So the International Congress happens every 4 years, apart from during wartime, and it just happened about a month ago, and that's where the Fields Medals were presented. But it started in the 19th century, and in the 1900 edition, David Hilbert, who was the foremost mathematician of the time, formulated 23 problems for the next century. And so I think that's one very good place to look to see what people thought was important at that time and how it looks now. So you can look at those problems on Wikipedia, or there's a whole book actually called, I think, something like Hilbert's List. It's quite a nice book actually. And roughly speaking, a third of them have been solved. A third of them turned out not really to be particularly good questions or a little bit vague. And a third of them are unsolved still today. And among the unsolved ones are some of the most famous problems in maths. The Riemann hypothesis is one of the problems that's still unsolved. Another example, which also maybe gives you an idea of what I mean when I say they were vaguely formulated, I think one of them was to find an axiomatic basis for physics. So I think anybody who's read any popular science books knows that that's still an unsolved problem. But yeah, I'd say that they've sort of 50% stood the test of time. So some of the ones that are solved you look back on now and you think maybe they don't look such central questions now, they look slightly puzzle-like. But other ones, I mentioned the Riemann hypothesis, and there are also a couple that are related to what's called the Langlands program, although it wasn't called that at the time because Langlands was only born in the 1940s or 50s or something. But they've turned out to be really central things in maths. So that's one answer to the question. You can also look back on what was happening in Britain at the time, which is quite a different story, and actually 100 years ago represents a real transition in British pure maths. Because for much of the 19th century, I think it's probably fair to say that pure maths, at least, was something of a backwater in Britain. People got very obsessed with things like the mathematical tripos, the exams in Cambridge, which became very, very fancy, sort of puzzle-like exams that sort of had increasingly little relevance to actual maths that people on the continent and elsewhere thought was important. So if you open up an issue of the Journal of the London Mathematical Society from about 1900 or something, to my taste at least, almost nothing in there is something that I care about. So there's sort of incredibly obscure questions like what happens when three paraboloids roll over each other in the presence of friction, and then they're all transported at 70 miles an hour down a tube and so on. And it's a similar story in pure maths. But around 100 years ago, a reform started happening, and foremost in that was G.H. Hardy, who was at Cambridge early on, but then came here to Oxford and was responsible for actually founding the Mathematical Institute, in effect, almost exactly 100 years ago, I think. And that's when we in Britain started taking on board what was fashionable elsewhere to a greater extent. And I think nowadays, well, maths is truly international. Maybe that's enough from me.
So, Mike, how is it in applied maths? What were the equivalent problems in applied maths 100 years ago?
Well, I guess 100 years ago, applied maths was largely about fluid mechanics, solid mechanics, lots of use of asymptotic techniques. I mean, my whole area of numerical algorithm development and scientific computing, just didn't exist. And so, just looking back over the last 50 years, the evolution of numerical algorithms and computing has just exploded. I started in computational fluid dynamics working at Rolls-Royce when I was 21. And the way that's revolutionized computational engineering. In the old days, you bent the metal, you tested it again, you saw if it was a better design, and now everything's done computationally. And so that emergence of computational engineering, and now it's come into all aspects of science. So it'll be fascinating to see where that goes in the next 50 years, next 100 years. Because I think it really has had huge changes in engineering and science. And numerical algorithms have been a key part of that. I mean, clearly we've benefited from the enormous increase in computational power over the last 50 years, but equally we've really benefited from improvements in numerical algorithms. Roughly speaking, as much improvement from algorithms as there is from faster computers. Trying to extrapolate forward as to where we'll be, I mean, it is so difficult to even look 20 years ahead, let alone 100. But huge changes.
And what about your field, Ruth? How has it changed in the last 100 years? I guess it hardly existed.
It didn't. I guess one of the things that I was going to say is that my field simply didn't exist that long ago, and it wasn't, I think, until work by people like Alan Turing that the really mathematical biology seemed to sort of have its beginnings. And even then, when Turing first proposed this model for pattern formation that we still use today, sort of people were quite sceptical of it, and it wasn't really well believed. So Turing proposed a model where essentially we got some chemicals. So you can think about it for skin patterning. We have some chemicals in the skin, and they react with one another, and they diffuse. And it just sort of turns out that if sort of parameters are in the right regions and the interactions are correct, then that can the sort of interactions and the diffusion can drive pattern formation. But it was maybe only in the last 10 or so years that we actually found a physical basis for that, sort of within patterning in the skin. So I think, really starting with people like Turing, mathematical biology began to evolve. Sort of moving forward gradually, people very much concentrated on using differential equations to model in mathematical biology. But again, really, as Mike said, it's with the sort of really significant increases in computational power that the field has really exploded, and now we can describe and develop models that describe sort of the behavior of individual cells in much more detail, and that's really revolutionizing the kind of predictions that we can make.
So what are the current areas that people are most interested in your field?
I think there's a huge recognition of the fact that we can maybe use mechanistic mathematical models to sort of within medical fields. So that might be within sort of looking at sort of blood flow within the heart or within other regions of the body, in particular in sort of treatments for diseases like cancer. So we can maybe think about using models to predict dosing regimen and things like that. So I think there's really significant applications in medical fields.
And what about you, Mike? What's the current hot topic?
So I think one of the interesting developments of the last 10 or 15 years has been the rise in stochastic models. So modeling including the effects of randomness. So 10 years ago, I moved over from doing fluid dynamics with jet engines into working in mathematical finance, where the randomness is coming from the day-to-day unpredictable variations in stock prices because of events. But stochastic modeling is very important in mathematical biology. you're probably used to the idea of describing chemical reactions with a system of ordinary differential equations. Well, that works when you've got good concentrations and everything's nicely mixed up. But once you get down to incredibly low concentrations, there's just the random events of molecules bumping into each other and undergoing a reaction. And so these stochastic effects become important in a lot of biological contexts. You've got random effects in things like oil reservoir modeling, where we don't know exactly what the permeability of the rock is. And so we model that as an uncertain spatial distribution. And then we want to be able to predict, the range of behavior that might happen with a particular oil field, given this stochastic model. So I would say that's one of the big developments in the last 10 to 15 years in applied maths.
And Ben, what's the current areas of pure maths that would attract the young people to work in? What's the equivalent of Hilbert's problems now?
Well, okay, so I mean, that's again a very big question. But there is a direct equivalent of Hilbert's problems. There's something called the Clay Mathematical Institute, which was founded by Landon and Lavinia Clay about almost exactly 20 years ago, because we're having their birthday conference here in 2 weeks. And it's now actually situated in this building on the 4th floor. And shortly after it was inaugurated, they had a list of millennium problems. And so there are, unlike Hilbert, who posed 23, they posed just 7. And also unlike Hilbert, they attach large monetary prizes to these. So they all come with a prize of $1 million. I think I'm right in saying that there's only one problem in common to the two lists, which is Riemann's hypothesis. And I'm certain that only one of the Clay Institute problems has been solved. That's the Poincaré conjecture, which is basically about understanding shapes in three-dimensional space. But it's interesting to look, perhaps the most conspicuous problem on the list that would probably never have occurred to people 100 years ago is what's called P versus NP, which is a very famous problem basically about how hard computation is. So we don't know how to prove that problems are difficult. We don't know how to prove that it's difficult to factor numbers into primes. We don't know how to prove that it's difficult to schedule things that solve the traveling salesman problem and related things. Everybody believes that these are hard problems, but we can't prove it. And that is something that's really arisen completely from scratch since the dawn of the computer age. To answer your other question about what people go into nowadays, well, that, of course, people go into the huge diversity of topics in pure maths. I think in pure maths, often the really great breakthroughs take people by surprise, and it's very hard to predict what the next one will be. So something that happened, I think, the year before last, as I normally do over breakfast, I logged on to the archive, which is where preprints come, and I saw this paper by a woman called Marina Wieslowska, who found the optimal way to pack spheres in 8 and 24 dimensions. And nobody had any idea that this was coming. We understood how to pack spheres in 1 and 2 dimensions in the 19th century. We understood the best way to pack spheres in 3 dimensions only after a huge amount of computer work at the end of the 20th century. And then suddenly one day she comes along and deals with 8 and 24. And those are still the only 5 dimensions we know. So I don't think anybody said here previously, I sort of feel that there's something bubbling. I think we're going to get dimensions 8 and 24 soon. So that's one example. But yes, what do people go into? I mean, there are areas that have fashions and so on. So the recent award of the Fields Medals somehow reflects certain mathematical fashions. The youngest winner, Peter Schultz, he seems to be somebody that everybody looks up to. I heard that there was a conference on his work for students in somewhere in America that attracted 500 people, whereas normally those conferences would attract 100 people. So obviously that's sort of a super fashionable area for people to go into right now. Also, a lot of people certainly do go into trying to study things like the P versus NP problem and computational complexity, partly because it's such a basic pure mathematical problem, but also, of course, it has enormous ramifications to the real world. I mean, if it was the case that P equals NP, so all of these problems that we think are difficult are in fact relatively easy, this would have It's vast ramifications for day-to-day life.
I always find it interesting that you get $1 million if you prove the Riemann hypothesis is true, but not if you prove it's false.
Is that the case? Really?
Prizes for a proof, not for a counter.
Well, it's a moot point, because I think anybody who's thought at all about it knows it's true.
I think the same is probably true in applied, Mike, that you don't know when the next big breakthrough is coming, right? Or what. A lot of the numerical algorithms that suddenly make something much more efficient, it's not that there was a prize to develop such a thing. It's just people gradually work on. I mean, the whole of applied maths is trying to make things more efficient, really. Right?
Yes, I mean, possibly to some extent, I would say that numerical algorithms get developed in response to a need. So you have a new area of application that throws up new challenges, and you get to the point where numerical computation using the existing tools and ideas is taking way too long, and people are scratching their heads thinking, well, we need to make more progress with the application. We need a technique which will go faster, and that's then what leads to the development of faster methods. I mean, if the existing methods are such that in the time it takes to go and fetch your coffee, the answer can be computed to sufficient accuracy, then you're not really motivated to go off and develop a method that does it in a tenth of the time.
But my experience has always been that no matter how much computing power you have, it's never enough. So
there's always some area of application where it's not enough, and you have people running calculations that take days, and so you've got other people who are busily thinking about whether there's some other approach that can be used, some better algorithm or better way of formulating the problem mathematically that will lead to a whole different avenue of attack.
One thing I found fascinating that I hadn't realized before we got together to have this discussion was that there are branches of mathematics that sort of die out and become unfashionable, and then other branches that come on. But I guess it's hard to predict what the unfashionable ones in the future might be, or where the new ones might come. But I guess there are one or two areas where they're hot today, and you sort of have an idea that mathematics is going to play a role. So we hear big data a lot. Maybe, Ruth, you could tell us how big data interfaces with your work.
So I think increasingly we are sort of trying to extract more and more quantitative data from experiments we're doing. I think that's probably true across the sciences, but I think in particular at the moment it's really true in biology, where we're seeing a real explosion in the sort of types of essentially techniques that we have to hand. So you can think about that in terms of the development of new microscopes, things like light sheet microscopes, which allow us to image in kind of ever greater detail, or we can think about that in terms of sort of single cell sequencing. So we can get gene expression data from thousands of individual cells. I think the real challenge for mathematicians then is to think about how to make sense of those data and how to interrogate those data to provide understanding of the underlying mechanism that's giving rise to a phenomenon. And I think there's two things really there. One is sort of, again, developing maybe sort of models that can interrogate that data and thinking about how to really interface the model with the data. And the other thing I think from my perspective is understanding how machine learning approaches can help us in that regard. So we might think, to go back to the gene expression or the single cell sequencing idea. So if we've got sort of gene expression readouts from thousands of individual cells, it's often very noisy data, it's kind of incompletely observed. How do we really make sense of that and understand what the underlying gene regulatory network is? And I think maybe there's some aspects of machine learning and information theory that are very useful in suggesting putative gene regulatory networks, and they're the kind of using these approaches to extract potential mechanisms can be very useful to us.
Well, one thing I find interesting is that you always think of data as statistics, but it's amazing how much it brings in pure mathematics now, that when data sets get so big, then topology starts to become important again, and people are looking at the topology of data sets and using techniques that would be in pure mathematics, but now with very real applications.
Very much so, pulling in a lot more areas of mathematics than we used to, really seeing, almost trying to understand whether we can make sense of the, like you say, the topology of the data without needing to understand sort of or look at every single detail maybe.
So one thing that seems to me to be very different now than 100 years ago is how specialized we are in mathematics. It always goes outwards, right? And so if you go back 100 years, then it was possible to work in more or less all branches. So somebody like Poincaré, about 100 years ago, would have had important results in pure and applied mathematics. But that doesn't really seem to be possible anymore.
Well, I mean, I think certainly it is true that pure mathematics has become extremely specialized in some parts. And there's still, some of the best people do still manage to sit across different areas. That was certainly the case with a couple of the Fields medalists this year, for example. They really did straddle different areas. But yes, I think it's, I wouldn't say it's a problem, but it's increasingly noticeable that pure maths is becoming incredibly specialized. And often these days, when I sit on appointments panels and so on, I don't understand what the person's doing. And so how do I make a judgment? Well, I have to take the point of view of somebody who I know, perhaps for some other reason, to have good judgment and so on. So you might ask, well, what's the point? And this is certainly a question I've asked myself a lot of times. And I think, I hope most pure mathematicians are ultimately motivated by one of a few different goals. So either trying to understand something that a large number of people think is a very basic object, like what's the structure of three-dimensional space, or is every even number the sum of two primes? Something that's sort of pretty basic, as opposed to being some extremely abstract object that you want to understand some tiny detail of. Or they maybe have more of an eye towards applications. Maybe they are perhaps motivated by the foundations of physics, or perhaps by the sort of applications that Ruth was talking about. But I've had a lot of arguments with people over the years about whether one should have those goals in mind. So I personally do. So there are a few. I would love to solve the Goldbach conjecture, that every large even number is the sum of two primes. That's something, I'm not working on it because it's too hard, but it sort of motivates the kind of things that I think about. But I know that there are other mathematicians who just pursue what seems natural, and they hope that it will eventually, just by following their nose, it will eventually come back to say something about objects that are perhaps more widely appreciated and understood. And there's a lot of evidence that that does happen. And I'm sure that a lot of the topology that goes into what you were talking about was originally developed as pretty abstract stuff that was quite hard to explain, even to people a little bit outside the area. But there's no doubt that it is becoming extremely specialized, and it can often be very, very difficult to talk even to colleagues about exactly what it is that they're doing.
So that idea of how you choose what problem to work on is interesting, and maybe we should go down the line and say, Mike, how do you choose what makes an interesting problem to work on?
So I guess I come very much from the applied end of applied mathematics, and so I'm generally motivated by an application. So in fact, my PhD is in engineering, so I really am sort of a hybrid between maths, engineering, and also a bit of computer science. So in the first 25 years of my research was on numerical methods for CFD, computational fluid dynamics for aircraft and gas turbine engines, collaborating with Rolls-Royce. And so there was a clear engineering goal there. Then I decided that that's becoming too much hard work, writing really large computer codes. And so I then looked around for a new field of application and decided to move into mathematical finance shortly before the crash. Purely coincidental, I'm sure. But then that led me into this whole area of stochastic modeling. And so I saw that as a growing area in applied mathematics, and so therefore I was interested in developing numerical methods to address the challenges in that area. So for me, yes, I'm always looking for interesting, challenging application areas, and then trying to respond to the needs in that area by developing numerical methods.
Okay. And what about you, Ruth? Is it similar?
Quite similar to Mike in many ways, although maybe mine splits between really, really true applications and methodology development. I don't always get to do both things together. So certainly identifying areas in which we need sort of new methods, new technologies in order to make advances is very important to me. The other thing is talking about or thinking about biological problems where modelling can kind of really make a difference. So as an example of some of my work, I look at migration of the cranial neural crest. So it's a population of cells early in development that migrates within the head region and essentially sets up a lot of the facial features. So if that process doesn't take place properly, we see sort of things like cleft lip or cleft palate. I think very much I'm motivated by the fact that if we want to kind of understand and be able to treat those kinds of problems, then we need to go back and think about how the embryo develops in the first place. So there's partly kind of real sort of true applications where mathematics can be useful, and also kind of identifying new technologies and hoping that I can use my new maths in those areas as well.
So one thing that has changed over the last 100 years is the application areas for applied mathematics. I mean, 100 years ago it would have been mainly solid mechanics and fluid mechanics and things like that, whereas now mathematical finance is relatively new on mathematical biology. What do you think the future holds for applications of mathematics?
Maths into everything. I mean, maths is just spreading out into all areas of science, and I think it's going to be interesting, actually. I ought to know the answer to this, but I don't. So I don't know whether for undergraduates in biology these days, whether A-level mathematics is now a requirement or not. But if it's not today, I'm sure it will be pretty soon. So I think lots of areas of science which maybe haven't historically had a huge mathematical content, I think now it's becoming essential. And certainly there's been a lot of effort over the last 20 years in taking people whose undergraduate degree is in the physical sciences and getting them to move into the biological sciences at the DPhil level.
So do you think social sciences is the next frontier? I don't want to mention Cambridge Analytica, but it seems like seems like mathematics is already in social science.
Actually, Cambridge Analytica is interesting from one point of view, that if you'd asked me 20 years ago whether mathematicians, say at the DPhil level, whether DPhil mathematicians needed to be exposed to ideas of ethics, I would have said that clearly that was irrelevant to mathematicians. Now I really think that that is something that we have to think about. That the same way that the engineers have courses looking at what it means to be a professional engineer and ethics and your responsibilities as an engineer. I think that is something that we have to think about as mathematicians now. Not just because of Cambridge Analytica. There are some other examples that have also made me think about that. Sorry, what was the question?
Do you think mathematics will have a role to play in the social sciences?
In the social sciences. Yes. I'm not sure that I'm capable of sort of following up beyond saying that. Yes, I think inevitably, there will be more and more sort of modeling aspects, coming in. That how accurate such models will be, and whether they will then be misused beyond the range of validity of the original modeling. I mean, there's always dangers of that. So, and I certainly wouldn't say that maths is going to take over, but I think it's going to be an indispensable part of lots of areas in a way that it hasn't been perhaps in the past.
So this might be a good time to open up to questions from the audience. Do we have a mic? Yeah.
Hi, I read maths and I work in IT, and every few years I read some pop science article that says quantum computing is going to revolutionise everything. Yet to be impressed. I noted it by your absence for over the next 100 years. Have any of you had any encounters with it, any hope for it, or have we been sold a red herring?
Okay,
I'm
so
going to push that to you,
I'm
Mike.
going to take that one. Yes. So anytime I'm asked about quantum computing, my answer is, which is a bit of a cop-out, is I don't see it having any impact on anything that I personally care about before I retire. And therefore I have not invested effort into it. Now, with my new hat on as department head, let me give a different answer to that. So we do have researchers who are very concerned about post-quantum cryptography. You know, that there are major concerns that quantum computing will enable the cracking of existing security, such that we need a whole new generation of techniques. So that's going to be the first application, I guess, of quantum computing is to the existing cryptographic security. I guess there's also quantum communications to protect end-to-end communication, so you cut down an intercept. But in terms of scientific computing, the sort of things that I'm working on, how far do I feel confident? Right now, I feel pretty confident saying for the next 25 years it's not going to have an impact. I think I wouldn't dare go to 50 years because, at that point, who knows? So how's that for an answer?
I guess you have to have the physics first before you have the mathematics, so it'd be very hard to think of a computer algorithm without having the hardware to run it on.
I mean, in general within IT, I would say there's probably 20 years at least between something that's working well in the lab to coming through to a commercial product that then comes out into general widespread use. And I don't think the current state of things within the lab is such that, and I see it coming out into widespread use within that 20-year time span. But yes, beyond that, because of what I said about my personal view, I simply haven't invested enough time and effort to really properly understand the possibilities to be able to give a really informed decision on a longer time scale.
I'm just intrigued about whether any of you have got views of if there is an end state to maths, whether in 100 years or 1,000 years or 10,000 years, where we've actually proved everything that's provable and we've proved that we can't prove everything else. And is there an end state?
That's a very interesting philosophical question. Ben, what do you think?
I certainly don't imagine that will be seen on the scale of a few hundred years. I mean, I can tell you right now a couple of problems that I'm absolutely certain are not going to be solved in the next 1,000 years. Are there infinitely many primes that are a power of 2 minus 1? Probably yes, but it's so the sort of probabilistic models for that are so finely balanced, and our understanding of primes is so weak that nobody will ever prove that. I could state some similar ones, but it's certainly there's no sort of empirical evidence for maths sort of folding in on itself right now. It seems to be that the number of open questions and open directions keeps growing.
I guess it's the same would be true in applied, that there's always a new phenomena to make a model of, and I can't imagine ever running out of things that we want to describe. So as long as physics is not finished, then I think mathematics is not finished for that reason. I guess a lot hinges on the imagination of mathematicians, right? To keep inventing the next bit down the path.
Well, I suppose there is a worry that we might end up in a situation where there are plenty of unsolved problems out there, but nobody can approach them. because you need to get to the age of 50 before you've even learned enough stuff to kind of even begin to think about the problem. Again, that's been a worry of people for many, many years, and that doesn't seem to be coming to fruition. I mean, so it seems to be, what happens is that very, very complicated machinery is built up, and it's gradually understood and then boiled down and simplified, and people manage to learn it and then apply it to other things. So I don't see at the moment much evidence of the frontiers receding to such a point that nobody can work on any questions. There's absolutely no evidence of that happening. So I'm not worried.
You're not worried, certainly until retirement anyway.
Pure mathematicians don't retire.
They just lose their faculties.
I read engineering. I understand there's a shortage of maths teachers in schools. So what sort of mathematics do you think is going to be taught in schools and even in universities in the next 100 years?
Who wants to go first?
Okay. So yes, there's a shortage of maths teachers in schools. What we do about that, I mean, my hope would be that that does get addressed. I guess there is talk, for example, of having increased salaries for maths and physics teachers. I don't know how much of that currently goes on, but I think there's talk about sort of in increasing differentials to try to address that situation. I mean, I certainly would hope that I mean, if this is what you're suggesting, that doesn't get in the way of the level of maths education in the schools.
My question is more about the content of the subject. What sort of mathematics is going to be taught? Because what people are learning in school today doesn't seem to have a very close connection with what we've heard this afternoon from the panel.
Yes.
So I think it's interesting. You have a finite amount of time in school, and you have to decide which bits of mathematics you want to teach, and which bits that the kids learn, or which bits are useful depends on what they're going to do next. So if you're going to go be a professional mathematician, you might want to know some bits very well, but lots of people don't go be professional mathematicians, so you want them to learn bits of mathematics that's going to be at least useful or give them an appreciation of mathematics in whatever they choose to do. And it is interesting how it changes over the years. It's a bit like Ben said, that complicated machinery gets boiled down so that it can then be, it used to be research level stuff, and then it gets boiled down so it can be taught to undergraduates. And some of that even gets boiled down and is understood well enough that it makes it down into A-level. So A-level syllabuses change as more modern mathematics gets in, and then something has to go usually. So we all complain that they don't know what they used to know, but in fact they just know different things.
To give an example, I have to say I don't really know what I'm talking about here, but I mean, for example, probability now features even on GCSE, I think, but certainly at A-level, and that's something that would not have featured probably 50 years ago in a more traditional A-level. But another point to make is that you can't run before you can walk, and you just kind of have to learn basic calculus at some point. And so that's why that's in the school syllabus, and it's also why we haven't really talked about it here, because we were talking about modern developments in mathematics and so on.
Another question over here? And there's one up the back.
So I actually have two questions, if I'm allowed, very quickly. One is about AI and whether you've seen any precedent, particularly on the pure side, of computers being able to genuinely contribute to maths. Has a machine ever proved anything that's then, genuine contribution? And the second question is about statistics, which is not really represented on the panel. And I was wondering what you saw the future of that being, particularly in the light of things like stochastic modelling. Where does classical statistics belong anymore? And do you see things like an encroachment of things like data visualization starting to encroach on what might have been a traditional sphere of mathematics to sort of validate certain statements based on data? Now people are validating them based on patterns they spot in just visualized data. And do you now see less rigour, perhaps, coming into certain fields?
So maybe I can just
You
quickly
take
answer
the
the first
first
question.
one.
So the basic answer to your first question is, so far as I'm aware, no AI has never proved any sort of theorem that anyone's interested in or wasn't able to prove themselves. I mean, I think the first step would be for AI to be able to do kind of A-level questions. And actually, that may also be the last step, because once AI can do A-level questions, I guess nobody has any incentive to learn school-level mathematics anymore.
So, okay, on the statistics side, yes, I mean, there are areas of overlap between the statistics department and what we do here in maths. In fact, at the time that this wonderful new building was being planned, there was a suggestion, an offer that they would come and share the premises, and we make it larger, to incorporate them. And at that time, I guess they were seeing themselves going down much more the bioinformatics line, linking into medical statistics, and so it didn't make sense for them to do that. But in fact, now the way things have panned out, there is a lot of overlap between the two. So yes, we haven't really sort of talked about that. Machine learning is one of those overlap areas. So within Oxford, we've got machine learning being done in computer science, engineering science, statistics, and maths. And without, I don't want to sort of draw too hard a line between these things, but computer science and engineering science are perhaps more focused on the application end of the spectrum, with engineering science, for example, doing a lot of things in the vision side, self-driving cars, things like that. Computer science working in machine translation, working in collaboration with Google DeepMind and activities there. And then in statistics and mathematics, we've maybe been slightly sort of later in getting engaged because it's taken a little bit more time to identify what is the core underlying mathematical principles. Where's the research to be done that will, lead to new theorems rather than new applications. But we do now have very active engagement in this area, and we are collaborating with people in statistics in that. So yes, our failure to mention statistics previously shouldn't signify that we don't have those connections.
Certainly from my perspective, I have a grant that one of the keywords would effectively be computational statistics, and a lot of the big questions we're asking is for the types of kind of more complex models that one might build. How do you use existing sort of computational statistics tools? And going back to points we talked about before, just because what exists at the moment is essentially not efficient enough to be feasible. So it's very much in there, although probably hasn't been mentioned.
Yes, I mean things like Bayesian approaches to parameter estimation in stochastic models. I mean that's the mainstream statistics, which is also being used here in the maths department. There's a lot of overlap.
There's one up there as well. Two up there, and one up there.
Hi, I have a question for Professor Green, if that's all right. It might be a bit specific, but I hope you bear with me. I think it should be interesting as well. A few years ago, there was a flurry of activity on gaps between primes, and I think it started with Yatang Zhang's paper, proving a bounded gap for the first time. And as far as I know, about a year and a half later, it kind of stopped, and it was culminated in the paper by the Polymath project, which reduced the gap from, it was 70 million or something, down to 6. But as far as I know, that's where it stopped. Do you know of any more developments since that time?
It wasn't 6, it was 246.
Oh, sorry. Well, I thought there was 6 under some assumptions, under the strongest possible assumptions of GRH, of the Riemann hypothesis and some other things.
Yes, 6 under assumption that might be more difficult to prove than the statement itself. But the answer to your question is that I believe nothing's changed since then.
You mentioned branches of mathematics which have stopped or ceased to be of interest. What did you have in mind, and what branches of mathematics do you see stopping in the next 50 years?
I think the first question is easier than the second. Let's do pure and then applied. Ben, what used to be fashionable but is not so fashionable in pure?
Okay, so it's not quite fair to say that it's no longer fashionable, but one example that comes to mind is the classification of finite simple groups, which was a huge project in the 60s and 70s and 80s. And the idea is basically, as it sounds, to classify all of these things called finite simple groups. And it turns out that there's a number of families of them, 6 or 7 or something, together with 26 sporadic ones, of which the largest is called the monster, appropriately enough. But at some point that basically got done, and so there's sort of no real incentive to go into that area and try and refine what was done there and understand it more now, because somehow the big goal's been taken away. And actually this is turning out to be a little bit of an issue, because when I said it was done in the 80s, it turns out that 1 or 2 bits weren't quite done. So it's this is an example of something that is not as fashionable as it was, so maybe young people aren't going into it very much. But unfortunately, we kind of need people to be able to understand it. So.
And all those people are now approaching retirement, isn't it?
A lot of them are. Yeah, one reason that sometimes areas become unfashionable because they just turned out not to have. Maybe it was thought that they had the hope of doing lots of amazing things. For example, at one point, I think it was thought that understanding transcendental numbers better might help prove Fermat's last theorem. And that just didn't turn out to be the case. So there was a lot of activity in the 60s and 70s trying to pursue that, and it didn't really go anywhere. So that's one way in which things can die out, if the hopes that they held didn't materialise. And another thing that can happen is that just all of the big things get solved, which is what happened for the finite simple groups. And to a certain extent, it's happened more recently with understanding three-dimensional spaces. That has also opened up huge numbers of other new vistas. But again, the big questions in terms of understanding three-dimensional spaces have been resolved. So naturally, at least some of the more ambitious younger people will choose not to go directly into that area at least.
On the applied side, there are techniques for various techniques of approximation that everybody would have known 100 years ago, and now you wouldn't bother because you can just solve it on a computer. So part-A approximation and things like that is not so, it's still useful, but nobody really knows it because they use other tools instead. I don't know if you can think of any other applied things that have died.
Yes, there's just less work using asymptotic techniques, particularly higher order asymptotics, because again, you just go to the computer. One of the concerns possibly for the future is the extent to which people just pick up packages, simulation packages, and they just use them in place of experiment, and whether that takes away the incentive to develop improved mathematical techniques, and also who in the future is going to be the core people who are developing these packages. There's a danger that I sometimes worry that people in my generation, there was a whole cohort of us who were really keen on on computing and getting in there and writing this mathematical software. And I'm not sure that that's such a popular thing to do these days. But these packages do have to be written by somebody.
And we should attempt to say what's going to die out, right, in the next 50 years. Who wants to put their head on the block?
I mean, I guess my feeling is that in applied maths, things don't die as much as taper. You know, so a new area sort of grows up, and then, you know, it sort of squeezes out other things. So each thing in its time gets sort of squeezed down, but it's a long taper rather than terminating as such.
I think maybe it's to do with the types of problems we're looking at, how much we know about a given problem, and as our kind of understanding evolves, we need new types of mathematics to bring in new types of mathematics to tackle those problems, and so we see it sort of ebb and flow a bit about sort of like that.
You might have thought that with 100 years of studying fluid mechanics that most of the problems have been solved, but there seems to be, it's not maybe not quite as active as it was,
Yeah.
but it's still pretty active. Ben, do you want to put your head on the block for pure or not?
No, certainly not. I do think, I certainly wouldn't want to predict whole areas dying out, but it's a very natural part of the whole process is that areas get totally expanded, huge amounts of stuff gets written in all the tiny little corners and furthest recesses. And that's an important part of figuring out what the lay of the landscape is. And then inevitably lots of that stuff will eventually be forgotten. But you wouldn't know which is the stuff that's destined to be remembered without having gone through that whole process. And even sometimes just the fact that a certain avenue is a dead end is a useful thing to have recorded for posterity.
Okay. Do you have another question?
On the PNP problem, are there any examples of an actual problem which was thought to be NP and somebody has come up with a polynomial algorithm to solve?
That is a good question. I don't think so. There are certainly problems. So recently something called the graph isomorphism problem was shown to have an algorithm that's not polynomial time but near to it. And that's the question of if I give you two networks on the same set of n vertices with lots of edges between them, can you tell if they're the same if you sort of remap the vertices appropriately? And I don't think that anybody ever thought that was an NP complete problem, but it was certainly maybe some people thought it was harder than it's turned out to be. So another question that sort of sits somewhere in between is the question of factoring large integers into prime factors. I personally, I don't really know what I believe. It certainly isn't as hard as an NP complete problem. I think it seems to be quite hard, but there are other people who think that that could be polynomial time. I think that's a niche viewpoint, but there are some people who think that. So there is the potential for that kind of surprise to happen.
Thank you.
No more questions. And that brings us almost, we're within 3 minutes. That was not bad timing. Okay, thank you very much.